So what I'd like to do is introduce the speakers for today. Dr. Marc Levitan, the National Institute for Standards and Technology in the Engineering Laboratory, and Nico de Toledo, and my apologies in advance, Nico. Both of them have been working on a project over the past multiple months at least, in documenting all events where critical facilities were hit by tornadoes. So the title of their work here is called Applications of the Storms Events Database and Damage Assessment Toolkit for Quantifying Tornado Impacts on Critical Facilities. So you'll see, you'll get a sense of how often they're hit and some of the implications in their research in terms of applications to communities and so forth, but also implications on the part of the National Weather Service, us that produce these surveys and create the storm events database and also use the damage assessment toolkit.
Thanks, Jim. So this is Marc. Just a bit about the genesis of this project. It actually began several years ago. As we were working through our efforts over the last decade or so to try to develop new methodologies to understand tornado hazards, to quantify those, and to develop tornado load methodologies so we could get those into the design standards and building codes for buildings. One of the challenges that we faced was not so much a technical challenge, understanding the tornadoes, and there was plenty of those, but sort of a perception challenge that, wait a minute, why are we going to put tornadoes in the building code in the first place? They're so rare, they're so small compared to earthquakes or hurricanes that we just don't need them. And so one of the things that we decided to try and do is to put sort of more of a specific face on it, is to try and understand and quantify what was the damage to particularly the critical facilities. And here I'm talking about schools, hospitals, fire stations, police stations, the things are critical to keep our society running. And if we could do that and show that the impacts on those facilities were similar to those that we would see from earthquakes and other hazards, that maybe that would help us socialize and be able to sell the need for getting tornadoes into the building code. And so that's what initiated this effort. We ultimately weren't successful in finding any good data sources to be able to quantify this for earthquake to make that direct comparison. But we had some good data that we found from the storm events database and damage assessment toolkit. So next slide, please. Okay, so just kind of acknowledge we had some co-authors and some students that have worked on this through the years. We'd also like to thank Stuart Hinson and Gord Strasberg for providing data and providing some review comments, and Camilla Young at NIST, and also Jim Ledoux were also reviewers on one of our papers and provided a lot of really great feedback on this and technical information on the interpretation and make sure we understand things and how they're laid out in the various tools. Next slide, please. Okay, so we're briefly going to talk about the storm events database mining and focus some on the using that to look at schools and how many schools are hit by tornadoes. The GIS analysis using the damage assessment toolkit and the impacts for these data, and ideas for increasing the utility for the DAT and the storm events database. Next slide, please. Okay, so why are we focusing on critical facilities? Again, these are kind of the backbones or the glue that holds our communities together. And we need these not only to provide the essential services, we need them to provide life safety protection for the people while they're in the facilities, and then also be able to operate and function after the tornado event. Next slide, please. Okay. So again, we're creating this database. Why are we creating this? We don't really have a good picture of understanding what's going on for the kind of the cumulative impacts. Sure, there's been lots of engineering reports, FEMA reports, NIST reports, other academic studies of individual tornadoes, and they'll look at, hey, this particular building performed like this, whatever, but we don't really kind of have the knowledge of this on a cumulative basis. And again, because there's so many tornadoes, and so many of them are some minor one and impacted a few buildings here and a few buildings here, but you add that up times 1,200 or more tornadoes per year, and then we get this cumulative impacts, which are not really well understood. And the idea that this data would be helpful for, one, development of the codes and standards in the first place, and then also for communities to make decisions on adoption of building code requirements, say for storm shelters in schools or for emerging design standards that we have in codes for tornadoes. Next slide, please. Okay, I'm going to go ahead and turn it over to Nico now, who's going to go through some of the details of how we were doing some of the mining and information from the SED and the DAT, and then I'll take back over at the end to talk about how we've used some of this data more specifically. So Nico?
So we chose the storm events database as our source for tornado impact data because it's the most systematic and comprehensive database of U.S. tornado impacts. And it contains descriptions of the tornado impacts in narrative format. It has two different types of narratives. One, which is called the episode narrative, which describes the overall weather event that spawned the tornado, and then the event narrative for each tornado that describes the impacts of the specific tornado. And it's important to understand that these narratives are not specifically designed to record critical facility impacts. They just capture the most significant impacts of each tornado. So the first phase of our research was focused on schools, and we mined these narratives from 1993 through 2020. We started at 1993 because the narratives from before then have not been digitized yet. So the mining process looked like this. We started out with 4 school keywords, which we chose after doing research on common school names and testing out what were going to be the most effective ones to use. And then we filtered all the narratives for those keywords and then read through each one multiple times to confirm whether it described a tornado hitting a school campus. And we defined schools as preschool through 12th grade schools. And then we recorded the school location, name, type, and other details such as the damage and whether the school was a part of a complex with other schools. And a big part of this process was filtering out positive results like school bus, damage that occurred off campus, or a description of the tornado passing near a school but not actually hitting the school. So through this method, we identified 669 schools hit by tornadoes from 1993 through 2020 for an average of almost 24 schools per year. And this count includes 21 schools we found online when trying to find additional information about the schools that were missing from the narratives in reports on tornado impacts and the news media. And high schools were most frequently struck, followed by elementary schools. So this map shows the school tornado impacts by state. These aren't normalized by population or area. These are just the total impacts. And Texas had the most schools hit by tornadoes, followed by Tennessee and Alabama. And we can see the impacts were concentrated in the U.S. Southeast. So we've also been working on mining the storm events database for fire, rescue, and EMS stations. This is still in progress, but from 1993 through 2011, we have identified that at least 88 of these stations have been hit by tornadoes for an average of almost 5 per year. And some of the most common damage was to communications equipment like radio antennas and apparatus and roof damage. So it's critical to understand that these results are a lower bound on the true number of critical facilities that have been struck by tornadoes. This is because the SED is not designed to capture all critical facilities struck by tornadoes. The ones that are in those narratives just happen to be mentioned there. And additionally, over 1,000 of the 37,000 plus records that we mined do not have any narratives. So there's no way to know if critical facilities were hit by those tornadoes using this data source. So to give you an example of how sometimes the narratives don't include all the schools that were hit by the tornado, in this image in red, we have a damage swath for this March 2020 EF3 tornado in Tennessee. And I have here circled in turquoise 2 schools that were mentioned in the narrative for this tornado. But then we can see down in the center of the screen this other school that's clearly in the middle of the damage swath, but was not mentioned in the narrative. And then, sure enough, we confirmed with online research that the school did have considerable damage. So to address this issue, we developed a complementary GIS analysis using DAT damage polygons, which are the same thing as damage swaths, but not to be confused with warning polygons. So the purpose of this method was to assess what is the proportion of the true number of schools that are hit by tornadoes that we've captured through the SED mining. So the way this worked is we used various school point location data sets to extract school building footprints from a data set of USA structures in the whole country, and then we intersected the footprints with tornado damage swaths from the NOAA's Damage Assessment Toolkit. I'll give you an idea of what that looks like here. So in green, we have a school point, and then we use that to pull out this yellow polygon for the school footprint. And then we drew a convex hull around this, and then we brought in a damage swath from the Damage Assessment Toolkit, and then we intersected those two layers, and in this case, we have a positive intersection. So then the final step was to confirm, just because we have a school intersecting with the damage polygon, was the school actually hit by the tornado? Because we'll get into this a little bit more, but the boundaries of these polygons are not always completely accurate. So we did this for 2 states. This is showing Oklahoma, the results for 2009 to 2020. We focus on those years because the DAT got introduced a little bit later than some of the data we had for the storm events database. So in pink, we have the schools that were identified through the storm events database mining. And then in blue, I have confirmed impacts that we found through the GIS analysis. So we found 12 additional unique results from the GIS analysis versus the 10 schools that we found through the SED mining. And 6 of the schools that we identified through the GIS analysis, we found again, those are in the yellow rectangles. Those are not part of the 12 unique additional ones. And then for Ohio, same color scheme. In pink, we have the schools we found through the SED mining. And then in blue are the 7 additional schools we identified through the GIS analysis. And in this case, there was no crossover. We didn't identify any schools through the GIS analysis that were found through the SED mining. And it's the same time period, 2009 to 2020. So looking at both of these states, we found that it looks like the SED mining captures only 50% of the true population of schools hit by tornadoes based on these 2 states. And the reason why we limited to these 2 states is because it required a time-intensive media verification to assess whether the schools actually were hit by tornadoes because they intersected with the polygon. Because our biggest challenge were that the damage polygons do not always have accurate boundaries because they're constructed in the field using varying levels of information, whether it's satellite imagery, which could lead to a really, or especially aerial imagery, could lead to a really accurate polygon boundary versus maybe a few points in the field. So it varies a lot. That's why we had to confirm the edge of the polygon is not always the true edge of the tornado's damage. So in the future, we're continuing mining the SED for fire rescue stations. We're planning to mine it for other critical facility types like hospitals, and we're planning to compare the number of school tornado impacts reported in the SED with those that we've been tracking in the news media for 2021 to get another idea of how many of the school impacts are actually getting recorded in the SED. And then our big goal is we're going to be publishing the Tornado Impacts on Critical Facilities database soon as a web GIS interface, which is going to map all these impacts and make it easy for the end user to visualize the local risk in their community. So I'm going to turn it over to Marc now for the impacts of these data.
Thanks, Nico. And next slide, please. Okay, and so you might think it seems like an academic exercise so far, but I'll tell you this has had very significant impacts and will continue to have very significant impacts moving forward. And so it's a busy slide here. Let me spend a couple of minutes here to talk about this. So previously, with the exception of storm shelters and nuclear facilities, we have not designed buildings for tornadoes. Tornadoes aren't in the building code. And so why would we expect that we would have good performance from our built environment if we're not designing for that hazard? Tornadic winds are very different from straight line winds. The engineering properties of those winds, tornadic wind structure interaction is very different from straight line wind structure interaction. Things like atmospheric pressure change, which increases has a component of increasing the loads, particularly as we build our buildings much tighter now for energy efficiency. The velocity profile, in tornadoes, we have a paper coming out soon looking at velocity profiles from radar data and other sources, where the wind speeds actually increase closer to the ground instead of decrease like a boundary layer wind. Duration, rapid changing direction. So there's so many differences between the wind characteristics for a tornado that the wind load provisions that we have in the building code don't really buy us much protection from even modest strength tornadoes. And so working on about a decade, we go back there, Nico, working on about a decade's worth of R&D, we developed new tornado hazard maps, new tornado load methodologies. We worked to get those into the middle picture there, into what's called ASCE 722. That's the ASCE, American Society of Civil Engineers. Their standard number 7, published in 2022 here, is minimum design loads and associated criteria for buildings and other structures. That's the backbone of what's used in the model building codes for determination of all the loads, from wind loads, earthquake loads, snow loads on the roof of the building, rain loads, all of the different loads. Those come from this ASCE standard. So we worked long and hard to get all this new methodologies for tornado hazard characterization, tornado load methods, to get those into the ASCE 7 standard. Then, as a separate process, we need to get that standard and those provisions from that standard adopted into the International Building Code. So let me just mention, so the International Building Code is what's called a model building code. And the idea is that that's the main model building code since the year 2000 that's used in most communities around the country. The building code by itself is just a reference book, just like the standards, a reference book that sits on the shelf. But once that book is published, then over years, then communities will start to adopt that as their local building code. And that may be, every state is different. So sometimes the codes are adopted on the state level, sometimes it's on the city level or a county level. Each state works a little bit differently. But the idea is, the first step is to get that from the standard. The second step is we got to get from the standard into the model building codes. Then we have to start to get that adopted down into the state and local level. And so in the proposal that we wrote, so NIST collaborated with FEMA and ASCE to write a detailed proposal to support the inclusion of these ASCE tornado provisions into the building code. And we had a section including that map that you showed of the school impacts. That was a surprising number for a lot of people. What do you mean we're hitting somewhere, at least 20 documented impacts of at least 24, 25 or so schools hit per year? That's kind of a visceral, it gets really provided like a visceral impact of, well, we're hitting that many schools now. That doesn't mean they're all completely destroyed or whatever, but that's how many tornado strikes there are on the schools that have that. Of course, some of them lead to significant damage or destruction or even fatalities. And so ultimately we were successful in getting these provisions incorporated into what will be published soon, later this fall, as the 2024 International Building Code. I'll also say that a lot of the same rationale that was used to support that was also submitted to the state of Florida, because Florida has a statewide mandatory building code, and that has already been approved for the tornado requirements to be in the 2023 version of the Florida building code. And so just briefly now, just the fact that we're going to have these tornadoes that are covered in the standard and that will be covered in the next edition, forthcoming edition of the code, that doesn't solve all of our tornado problems. So the tornado loads in ASCE 7 are required for basically what we call risk category 3 and 4. We have 4 risk categories that go from 1, which is low risk to human life, and temporary facilities and agricultural facilities that are not occupied all the time, et cetera, through 3 and 4. The tornado load requirements apply to risk categories 3 and 4, which are kind of high occupancy buildings, theaters, assembly buildings, as well as the critical facilities, schools, fire, ambulance, police, hospital, those kind of things. and those would only apply in the tornado-prone region, which you see at the bottom left, and that's based on the return period analysis and reliability analysis of tornadoes. We do have tornadoes out west of the Rockies, but they're much fewer and farther between and much less intense. Now, the tornado speeds that we're designing for in the ASCE 7 standard range from 60 to 138 miles per hour, which is approximately sort of EF0 through EF2 type tornadoes. Now, EF0 through 2 is about 97% of all tornadoes. And the specific design speed that you would use for a particular building would depend upon where you are located in the country, what this risk category is, and this plan size and shape of the building or the facility. So that plan size and shape has a significant impact on the likelihood that you're going to get struck by a tornado and those tornadic winds. Next slide, please. We've also used these to support, and this wasn't, I hadn't thought about this when we first started the project. We were thinking about getting things adopted into the IBC, but in terms of now that we're seeing applications in terms of local adoptions of tornado resistant criteria. In Oklahoma, which has some of the most intense tornadoes and more tornadoes per square mile per year than almost any other place on earth, when they adopted the 2015 International Building Code as the statewide building code several years ago, they amended out the requirements to have storm shelters for schools. And then when they updated the adoption for the 2018, they said, okay, well, we're going to keep those requirements in. And then several months later, they had a move to have a moratorium and to strip those shelter requirements back out of the code. We were contacted, asked to provide some information for people that were giving testimony to help oppose the proposed plan to eliminate the school shelter requirements. So Nico put together this map, and this was from some SED analysis, and we also had some local information from Oklahoma. This was done prior to when we had done the GIS analysis. It would have been more impactful because, as Nico showed, we found a number of other schools as well that were struck by tornadoes. We noticed a school in Sweetwater, the same school, was even struck twice by a tornado. So this kind of visceral information that lets people and decision makers know that tornadoes are not that rare. I mean, you hear about them on the news occasionally. Well, in Oklahoma and Central U.S., you hear about them more than occasionally, but still, you just don't understand the full range of these impacts. And so certainly this information plus testimony of others, they were successful in blocking the attempt to overturn the requirements that new school construction in Oklahoma would include tornado shelters. We've been contacted by FEMA to provide similar maps for a couple other states. Unfortunately, Ohio has recently made a decision that they're going to take out the requirements from the building code for storm shelters and other states, and so there may be changes along the way. But so key impacts as we work as states are going through these decisions to whether they're going to adopt the latest version of the code, whether they're going to adopt the 2024 IBC. Hopefully they're not going to amend out those tornado requirements, which can always happen with these local adoptions. So this online database that we're creating that will hopefully be very helpful for local, state and local jurisdictions to be able to better understand their tornado risk. The next slide, please. Okay, so just a couple of things that we've come across doing our work here. Would like to share with you of some ideas for increasing the utility. One, if we could improve the consistency of the DAT implementation. For example, not all the counting warning areas have damaged polygons for most of the tornadoes. I'll show you an image of that on the next slide. And it'd be helpful for researchers if there's a way to assess the uncertainty in some of these polygons. As Nico said, sometimes perhaps if they're based on aerial imagery and extensive ground surveys that we have sometimes for certain tornadoes, then there's more certainty in those boundaries. Otherwise, perhaps it was just based on maybe there was no aerial or satellite imagery for that particular tornado, and it was a more sparse ground survey. So if there's some way to be able to capture or characterize that, so we have an idea of what the uncertainty is in those polygons. Next slide, please. For an example for that first bullet, and this is a plot for a few years of tornadoes from March 2000 through April 2023. And so we can see in most of the county warning areas around the perimeter of the image, we see lots of tornadoes. And then we've got a few kind of in the middle there where Memphis and Little Rock and others. And we sort of just don't have any, and that's not quite Mother Nature. Now there may be track lines in there and tornado reports, whatever, but we just don't have the polygons in there. And so these polygons are critical, and not just for this application we're talking about, for the applications of developing the next generation of tornado hazard maps that will go into the next editions of standards and building codes, to be able to have this detailed mapping, to be able to have these polygons, to understand the swath areas is critical to understand then the point strike probabilities and then the aerial strike probabilities. Next slide, please. Another would also be super helpful is if we could digitize the pre-1993 episode and event narratives. Back when I was a professor at LSU a long time ago, we traipse over to the library and get the old storm events books off the library shelves from the references section and go and photocopy those and whatever. But I know at some point there was an effort to digitize, but it'd be great if we could digitize those pre-93 event and episode narratives. Are super useful. And also, if possible, to incorporate additional critical facilities in the damage surveys and the narratives, just because, again, they're such important facilities, and those are the ones that are primarily covered currently, that will be covered in our codes and standards. And so to be able to have that better understanding of the impacts on those, that's going to help us improve our codes and standards and improve the adoption of our codes and standards. Next slide, please. Okay, so if we just kind of summarize some of the key results we found, is that we think we have, at least just from the SED, we can document about 24 tornado strikes on schools per year. But then looking at the Damage Assessment Toolkit, finding that true number is probably closer to about 50 strikes per year across the country. So it's a pretty large number and an impactful number that people are surprised that it's so high. These data are helping to increase the state and local adoption of tornado-resistant design standards and storm shelter requirements. And further improvements to the DAT and SED can enable more accurate and efficient tornado impact analysis that would further enable local decision makers to make these informed decisions about their risk when they look towards adopting the tornado shelter requirements and these new tornado-resistant code requirements in 2024 building code. So with that, I think we'll go ahead and wrap it up. I'll just mention here, there's some references. We do have one paper on this that was published last year. And if we go to the next slide, Nico, there's a QR code there on the bottom if you want to scan that, and you can pull down the paper that describes more about the methodologies that we use, the data sets, those sorts of things. And I said we'll hopefully by the end of this year we'll be publishing the at least the first edition of our critical facilities database, and hopefully with a web interface, a WebGIS interface on that. So with that, I guess we'll open it up for questions. Thank you.
Great, thank you, Nico and Marc.